Let's talk about electrochemistry today and how it applies to batteries, electrolysis, reference electrodes, and then basic electrochemistry experiments. So to begin with, let's talk about batteries and electrolysis. Now, we've all used batteries on a regular basis in our phones, in our laptops, everywhere. They are everywhere. They're wonderful for storing energy. And so as such, I believe we should understand at least the basics of how a battery works and what is the chemistry that makes them work effectively. So here is a picture of a basic battery where you've got the cathode is the positive charge at the top and the anode is the negative. So what is happening here? Remember, your anode is oxidation. And so in an oxidation reaction, you are producing electrons. So just by convention, our cathode here is our positive and our anode is our negative. So what is happening at the anode? We've got oxidation of zinc to zinc oxide where we are releasing 2 electrons. So if you take and you look at this anode, we've got this collector pin here in the middle and then it's surrounded by this zinc powder. So this is the zinc solid in the reaction, and whenever it is getting oxidized, it's releasing electrons which are coming here, and this is sort of like your electron wire, right? So remember, electrons flow from your anode to the cathode. They're flowing through this collector pin, both sides of the wall to the cathode. Okay, so now what's happening with the cathode? The cathode is reduction, and so in this case, it's shuttling these electrons through the cathode to this dark purple that you see here, which is your manganese dioxide, and that is what is going to get reduced. And so we have manganese dioxide reacting with those electrons that are supplied from the zinc on the inside, and it's going to react and going to become reduced. So then this paper right here is basically acting like your salt bridge. So it is going to be physically and chemically separating the 2 species from each other. So that way there is a potential difference between them, and that's what's causing the flow of electricity. And so once again, you hook anything up to the top and to the bottom, and now you're going to have flow of electrons through whatever the circuit is that you've entrapped. So now if we look at this from the standard reduction potentials, we can just take the cathode minus the anode, we can get the standard reduction potential for the cell, and we can see that it's about 1.41 volts. And if you look up a AA or a AAA battery, they are typically 1.5 volts, and the difference here is accounted for in the Nernst equation, where the Nernst equation takes the concentrations of each of your species into account. And so that gives you your differences here than just the simplistic view and overview we see here. But main takeaway from that is that you have to produce the electrons, and that's typically going to be your positive terminal, at least from the chemistry perspective. Alright, so then how can we kind of use that to predict what's happening? Using these balanced half reactions, let's look at water. How can we produce water using oxygen and hydrogen? And then we're going to compare that to what we just learned about the battery. So to begin with, let's just balance these half reactions. So if I told you that this is a galvanic reaction, we're going to produce water spontaneously by combining oxygen and hydrogen together. Balance the half reactions and tell me how many electrons are transferred. This is what you would do. So these are the steps that I use in balancing a half reaction, so we're just going to go through those together. So the first step is to write the half reaction. So I separated oxygen and hydrogen from each other in this chemical equation. Then I'm going to balance the top one first. So I'm going to balance elements other than oxygen or hydrogen. That's all I have. So then I balanced oxygen by adding water. So I'm going to need to have 2 waters as a product, so I'm going to balance those. And then it says to balance hydrogen next by adding H+. Notice I have 4 hydrogens on the right, I need 4 hydrogens on the left, and then I'm balancing my charge by adding electrons. So in order to balance that out, I'm going to add in 4 electrons on the left. Next, I'm going to do the exact same process to the next reaction. So balance elements other than oxygen or hydrogen, check. Balance oxygen by adding water. So I need to add water to this. I'm going to add it to the left side. Now I need to balance my hydrogens. So I needed to add 2 more hydrogens to the right side to balance that out. Then I balance my charge by adding my electrons. And then the very last step says balance the electrons across the reactions, which that means that I have 4 electrons in the top reaction, 2 electrons in the bottom, so I need to multiply that whole bottom equation by 2. But before I do that, I'm going to notice I have water on the left, water on the right, so I'm going to cancel those out, which that leaves me with When I multiply it by 2, 2 hydrogen gas plus 4 hydrogen ions plus 4 electrons. And now if I add my two reactions together, I will see that this does in fact produce this equation that I started out with. Alright, so then we need to see, is that really galvanic or is it electrolytic? And how we check that is by looking to see what the potential, the standard reduction potential for the cell is. So if we look up at our chart and we look up the standard reduction potential for each half reaction, we'll be able to find each of our half reactions. We've got this oxygen there at 1.23 volts and the hydrogen form at 0 volts. Now you may have noticed, wait, that second one, 2 H pluses. I have 4 H plus in my equation, and I also have 2 H2. Well, is that the same thing? Are these two right here the exact same potential, or do I need to do some kind of multiplying? Absolutely not, never. Okay? Anytime you multiply the equation, the standard reduction potential is still the exact same. Okay? You're not changing the energy that's required to release an electron. You're just changing how many electrons are released. Okay, so don't ever change it, leave it the way it is, and now we can go cathode minus anode to figure out what the voltage of the cell is. Alright, and if E is positive, that means delta G is negative, so this works out. This is a galvanic reaction. That means that if you have hydrogen and oxygen, they can spontaneously produce water. And so here you can see the anode on the left is having an oxidation reaction where we're producing electrons. Electrons are flowing through the wire down to the cathode. The cathode's accepting the electrons and oxidizing to produce water. Alright, so what's going to happen then whenever we do it the opposite way, where we require electricity in order to create chemistry? Everything's going to flip around. Okay, and so with that being said, my oxidation reaction now is going to be with my oxygen and my reduction is going to be of hydrogen. And so now my cell potential is going to be negative 1.23 volts, which means my Gibbs free energy is positive, which means it's non-spontaneous. Alright, so this is my reaction. I wanted to build up to this so now we can compare it to the battery because we need to make sure we know what terminal do I expect stuff to produce at, and how does all these electrons flow, because it's important to be able to figure out where are electrons being produced and where are they ending up and how is the reaction created. Alright, so how does this electrolysis of water work with the battery? So here's what we should have seen whenever we did the experiment the other day. There should have been twice as much hydrogen being produced at the negative terminal of the battery, and the positive should produce half as much. And so what we might have seen is that we saw more bubbles. We thought at the positive, but really those are just bigger bubbles. If we had just waited, we would have seen that the actual volume at the top of the test tube that collected would have been twice as much. And we will practice this in class whenever we see each other again. Okay, so twice as large of a bubble should appear at the anode, which is negative. Now remember that the cathode by convention is the positive terminal and the anode is negative. And so what's happening is that by convention the anode, which is oxidation, releases electrons. So now we have electrons flowing, which are going to form with the hydrogen ions that are in the acid inside of the water. They're going to form the hydrogen gas. Twice the volume. Then water is going to be oxidized to release 4 protons and 4 electrons. And so you have a constant flow of accepting electrons and releasing electrons, and therefore current is flowing. We have a nice electrolysis of water where water is being continually converted into hydrogen and oxygen, but it is not spontaneous. It required the electricity that was provided by the 9-volt battery. And so in this case we're able to see how naming things properly, like with the cathode and the anode of the battery, makes it so you can understand where the electron is coming when it goes into the electrolysis of water and where it's going. Okay. So that being said too, that whole salt bridge idea is important because with rechargeable batteries came a lot more technology and we were able to do a lot more with some of our devices. For instance, I know I have used a camera before that I stuck alkaline batteries in, and then those batteries were dead in like an hour. Well, when I stick a rechargeable battery in, it lasts a very long time, and a whole lot of that is based on the mechanism for both charging and discharging of the battery. And so in this case, the ions for the alkaline battery are not allowed to go across the paper barrier. But in rechargeable batteries, they somehow allow for the transport of those ions, which allows you to regenerate the original chemicals. Okay, and so in each case, it's either a matter of, hey, these are acting as a battery, therefore this reaction is galvanic. Oop, now I need to recharge my batteries. I plug it into the wall. The wall is supplying my power, so now it's electrolysis, pushing the lithium back to where it needed to go. Okay, but the idea is still true that basically these alkaline batteries have some kind of internal resistance, and that internal resistance is going to increase, preventing, those flow of electrons between the anode and the cathode, not electrons, flow of ions between the anode and the cathode, and that's going to continue to increase with time. And so current is also, because if you're increasing your resistance, that V equals IR, then your resistance increases, your current is decreasing. Okay, so then, because remember your potential is staying the same because you still have the same chemicals involved in the reaction, so your potential is going to be held constant. Okay, but rechargeable batteries, on the other hand, they have half the resistance, and it's able to maintain the current requirements of the device. That it doesn't have that same problem with the resistance, internal resistance, increasing over time. And so because of that, devices such as cameras that are trying to maintain a constant power output, they'll actually last a whole lot longer. If you have time, go look at this article on how stuff works. It's a fantastic article that can tell you so much more about rechargeable batteries, because I've only touched on the bare minimum of rechargeable batteries. There's a whole bunch of neat stuff out there. Alright, now let's do some comparison of reference electrodes. In a previous lecture, we discussed silver chloride reference electrodes, and then also calomel or mercury electrodes. And so with these electrodes, it's really important to think that they are just used as a reference, meaning a comparison. And so whenever we're reporting something as, oh, I noticed the voltage of 1 volt, that's always 1 volt in comparison to something. And that comparison is typically done to a reference electrode. And so we looked at the reference electrodes earlier, but we didn't look at the math on how you would go from, oh, I used a standard hydrogen reference electrode and I measured this voltage, but my friend used a silver chloride. Did we measure the same voltage? And so being able to make that comparison is important. So these were the two electrodes we looked at before, but how do we go back and forth between them? So here's what I want to do is, let's say we're using a standard hydrogen electrode. And we want to measure the copper 2+ to copper transition. So that, if you look that up on your standard reduction potential chart, that should show up at 0.339 volts versus a standard hydrogen electrode. But my question is, what if we are using a different electrode? What if we've got a silver chloride? Is it still going to show up at 0.339 volts? No. Okay, so how do we do this math? So if I look at the difference between the standard hydrogen and the copper, it's going to show up at 0.339 volts. And I always draw this timeline because it just helps me out. It helps me figure out, is the number, should it get smaller? Should it get bigger? What's going on? Okay, because you can tell here that if I just took 0.339 minus 0, that gives me 0.339 volts. Now what about for between silver chloride and copper? So if silver chloride is my reference, that means essentially I'm setting that up as 0. So that's my 0 point. So my first question is, my copper 2+ to copper, is that going to show up more positive than silver chloride or more negative? And you can tell quickly that it's more positive. And so how much more positive? So in this case, I just took 0.339 minus 0.197 and got 0.142 volts. And so that's where it would show up. And so if silver chloride was at your 0 point, which it is if it's your reference, then my copper would show up positive 1.42 volts away from it. Okay, and then my silver chloride, you can do the same thing where you're asking yourself, okay, where is it going to show up? And you'll notice it's still going to show up positive, just not as positive, because my saturated calomel electrode is a lot more positive than either my silver chloride or my SHE. Okay, and so just looking at this relationship between them, if we're all measuring the same couple, but we're not using the same reference, we can still make comparisons. And so this is really helpful if you're reading a paper that's using some reference that's different than the one you're using. Alright, so give this a try. What would your cell potential be if you use the saturated calomel reference electrode and you used your silver chloride as your working electrode. So what if now I'm not interested in the difference between copper and my SCE? I'm looking at the difference between SCE and the silver chloride. So meaning, if SCE is my reference, boom, silver chloride, is it going to be negative or positive of it? I hope you realized it would be negative it. How much negative? That's essentially what I'm asking. And so in this case, it would show up negative 0.044 volts compared to the SCE. So in this case, SCE is set to 0, and then I need to figure out where is my lead on this chart. So I would look up my lead on my standard reduction potential site, and I would notice that it's negative 0.13 volts. And remember, that's compared to the standard hydrogen electrode, because everything is compared to that just simply by proxy that it was figured out first. Okay, so I'd put it here on my timeline, and now I just need to ask the question, what's my difference here? And so I hope you realize in this case you would add your 2.241 plus 0.13, and it's going to be negative, okay, or negative 0.371 volts. So however you need to do it, figure out what is going on here and how you're able to make those comparisons, but it'd be helpful if you're able to tell, oh, lead is supposed to show up at negative 0.13 volts compared to my standard hydrogen electrode, but compared to my standard saturated calomel, it's going to be negative 0.371 volts. Alright, so now let's look a little bit closer at specific subtypes of electrochemical experiments, because everything we've done so far has just been the precursors, but let's look at the real world. How is electrochemistry typically used in the real world? So to begin with, in the last couple slides, I used some names that you are a little familiar with probably of a reference electrode, but then also I used a word called working electrode. Working electrode is the place through which we are taking the chemistry measurements. And so typically we only care about what's happening at the working electrode, but we'll use that reference electrode for comparison. So it's sort of like when we were looking at the copper ion selective electrodes or the calcium ion selective electrodes. We didn't really care about the chemistry that was happening at the reference, but you needed the reference there just to hold your electrode stable. Okay, so reference, making it stable. Your working that's where the reaction's happening that you care about. Okay, but just because things can get a little more complicated, we needed to throw in a third electrode. So in the top circuit, this is just a 2-electrode system where you have a working and a reference electrode, and what happens is the current begins to flow through the reference and the working. And what happens with this, if you have too much current, you can degrade your reference electrode with time, and so you're destabilizing it. And so in order to prevent this, we added in a auxiliary electrode, and that's sometimes also called the counter electrode. And what happens is the current now can flow through the working and the counter electrode predominantly. You just have minimal current flowing through the reference, and that makes it so that the voltage differential can still be maintained between the reference and the counter and the reference and the working electrode, but the majority of the current now can pass through the auxiliary, thus protecting your reference from degradation. But the whole idea behind this is that you have this third electrode that literally its whole job is to prevent the reference electrode from getting damaged, so it makes things become more stable with time. Alright, this method is called cyclic voltammetry. It's one example of how electrochemistry is used in the real world of research and in industry. In this case, the reference is once again used to make sure you know the voltage that's applied at any given moment. If it's set up correctly, you can ignore the counter electrode, and the current mainly travels between the working and the counter electrode, but the potential is what is interesting here, because as chemistry happens, the potential difference between the working and the reference is going to be directly due to the current that flows between those two. And so what happens in cyclic voltammetry, that as the voltage changes, the current passing between the reference and the working electrode is measured. And so you end up with something like this, where if this bottom axis is time, and this top here is going to be your voltage. So you're going to slowly change your voltage with time, and then you're going to turn it back and go the other way. And so what happens, each of these letters correlates with a point on this. This is a duck or a cyclic voltammogram. And so it starts out where maybe you're at like a voltage of 0, and then you're slowly increasing your voltage. So you're going from a negative or from a 0 potential to a positive. And what's happening is you're not having really any changes in current, no changes in current. Ooh, now all of a sudden I have a huge change in current, and it's going back to where it started. And then you're cycling back, you're going back to where you started from as far as voltage goes. So now voltage, whee, is changing, it's going back to where it started, and we're here. Okay, and so what happens is we're figuring out how does the current change with time. So you don't see time at all in your raw data graph, but time was used to cycle it. And so you're changing it some number of millivolts per second, and then you're recording what is the current. So this is controlled by the reference, really. What potential is being applied is controlled by your reference. But then the potentiostat measures the current that's produced. And so when the current's produced, it's sort of like saying, hey, my standard reduction potential says that I don't have enough energy to strip away an electron yet. Nope, not enough energy. Oh, hey, now there's enough energy. Now electrons are getting stripped away like crazy. Therefore, I see this peak. And this peak here is correlating with oxidation, whereas the opposite happens here. Now enough energy is happening where we're able to reduce it. Electrons are flowing back into whatever my substance is. And so what you're seeing here is peaks that may not look like peaks to you, but they are peaks here and here, whereas these are more like flat regions where the current is not flowing as much. Okay, so what happens in this case, you're able to directly extrapolate standard reduction potentials from these, where let's say this is one half and this is the other half. This part here in the middle, if you notice, this E0 is the difference between the average of the two peaks. So let's say this was 1.5 and this is 1.6, then your standard reduction potential will be 1.55, okay, or the average of the two. Okay, so that's where these standard reduction potentials come from, and that is also why I tell you do not flip your voltage for your anodic or your cathodic current, because that would mean this peak is way somewhere crazy different. Okay. These two things here are two parameters that let you tell whether a reaction is reversible. What it means by reversible is, can you oxidize it and then turn right back around and reduce it? And if you can do that with ease, then it should be a very symmetric peak, and your two peaks should be very close together. How close is very close? Oh, about 59 millivolts per mole of electron. Okay, so if these two are close together, and if the peaks are very symmetric, so this one is about as high as this one, then you're going to have what's called a reversible peak, and we'll look more at that here in a second. And so with reversibility, when we're asking this question, can you see two peaks and are they symmetric? If equation 1 or 2 are true for the relationship, then the reaction is electrochemically reversible. Okay, and then equation number 3 is simply used to find the standard reduction potential for a reaction. Alright, let me ask you a question. If you're shown these two cyclic voltammograms, which of the chemistry is more reversible? Do you think the peaks for A or the peaks for B are more reversible? And could they potentially be the same reaction? What do you think of that? Alright, so let's answer the first one. A, which is more reversible? Well, they're both pretty symmetric, meaning this peak is has a current of about -8. This one has a current of about 5. So so if you look at equation 1, IPA over IPC is going to be approximately 1. It's going to be a little less than 1 because your oxidation peak is bigger than your reduction peak. But same thing can be said for this one, because it's like at negative about 12 and positive about 10. And the reason why it's still about equal is because really you're taking the difference between the baseline. So meaning this one, see, it's a little bit above it, so it's about positive 2 to about negative 12, so that means the difference here is about 10 microamps, and then same thing for here, it's going to be about 10 microamps. And so IPA over IPC is going to be approximately 1 for both sets of graphs. Okay, but what about that second equation, the EPA minus EPC? So let's approximate that. So IPA, so A is anode is oxidation, that's down here, at least for chemists. For engineers and physicists, they do this completely opposite. So down here, we want to look, and that's about 0.35, something like that. And then up here for the blue, it looks like about 2.22, something like that. So we're looking at about 100 millivolts, give or take. This one is going to be at about 0.45 and about we're just totally approximating here, 1.5. And so you can see that the difference between these two peaks is much greater than the difference between the blue ones. And so keep in mind, because the difference is greater for A than it is for B, then that means that B is more reversible than A. All right, could they potentially be the same reaction? You answer that with the third equation. If EPA plus EPC divided by 2 is approximately the same for each of them, then it could theoretically be the same, okay? Because that means the center of the two ducts is approximately at the same point, which is true. They're both centered about the same region here, around 0.3, so they could theoretically be the same potential reaction. All right, so how do we use this? We can use this in a couple ways. One is through amperometry. So amperometry says you need to figure out first, where does the current change, and is that a selective location? Because the more positive you get, the more stuff will naturally be able to be, converted. The more negative you are, the less stuff will happen at lower potentials. So you pick something, and let's say I picked a peak here, 0.8 volts. Maybe I hold a potential, so I'm applying 0.8 volts consistently for a long period of time, and I'm just saying, how does stuff change? Something like that is going to be this glucose oxidase sensor. And so the idea with the glucose sensor is that you're utilizing glucose oxidase as a mediator. So glucose turns into gluconic acid as glucose oxidase turns into the reduced form of glucose oxidase. Then the mediator picks up those electrons and it becomes reduced, and then at the electrode surface takes the reduced form and oxidizes it back to the oxidized form, thus releasing electrons into the surface. If you set one potential at the electrode surface, and you set it and you leave it there, and then you check how much current is flowing, that current is going to be proportional to the thing at the very beginning of this chain, glucose. And so it was cyclic voltammetry followed by amperometry that made it so we could detect how much current is flowing based on how much glucose is present. So all of this was foundational for diabetes research. Alright, here's a couple other examples. I just wanted to show you a couple of examples of what peaks might look like in different experiments. So up at the top, those are differential pulse voltammograms. So basically, remember the waveform I showed you for cyclic voltammetry, the up, down, up, down? This has a different pulse, but the idea is still the same, that we're measuring some kind of potential and getting a current read off of them. Or down here at the bottom, anodic stripping voltammetry, and that is where you apply a potential that causes the species to deposit on the electrode surface, and then you apply a different potential and it causes you to strip away that chemical species. And what's really cool about both of these techniques is they can be parts per million or parts per billion sensitive, which makes them extremely sensitive techniques that are really good in like wastewater treatment, that kind of analyses. But that is all. We can talk more about specific applications of electrochemistry on Friday, and we can dig more deeply into any of this slideshow that you would like to dig into.